Hello and welcome to Kognito Key. Today, we are going to dive into a really brilliant piece of engineering. It's a device that solves a huge problem for so many industries, which is how do you measure the flow of liquids that would just destroy any normal meter?
Just think about it for a second. How would you measure the flow of something really thick, like a slurry, or a liquid so corrosive, like an acid? You can't just stick a regular meter in there. Anything with moving parts would get clogged up or completely eaten away almost instantly. So what do you do with these really tricky fluids?
Well, the answer is so elegant, it's actually ingenious. It's a device with zero moving parts, none at all. It just relies on a fundamental law of physics to do its job. And this amazing device is called the electromagnetic flow meter, or as most people call it, the mag meter.
Okay, so what exactly is a mag meter? To put it simply, it's a device that measures the flow rate of any fluid that is electrically conductive. Now, that term, conducting fluid, that's the real key here. It's the secret to the whole thing. All it means is that the liquid itself can carry a tiny electrical current, and that one property is what makes this whole meter work.
Right, so the big question is, how on earth can a device with no moving parts actually measure flow? It sounds a bit like magic, doesn't it? Well, the answer isn't magic, but it does lie in a really beautiful piece of physics that was discovered almost 2 centuries ago.
It all comes down to something called Faraday's Law of electromagnetic induction. Now, this single principle is huge. It's the foundation for things like electric generators and motors, and, you guessed it, our very clever flow meter. The law basically says that when you move a conductive material through a magnetic field, you generate a voltage. Let's break down how that applies right here.
Okay, so it really works in 3 pretty simple steps. Step 1, you need a magnetic field. The mag meter has these powerful magnetic coils that are wrapped around the outside of the pipe, and their job is to create a constant, steady magnetic field that goes right across the path of the fluid. Step 2, you need a conductor that's moving through that field. And this is the really brilliant part. The liquid itself is the conductor. So as the fluid is flowing through the pipe, it's acting just like a wire moving through that magnetic field. See how clever that is?
So, if you put those two things together, what does Faraday's law tell us is going to happen next? Exactly. A voltage gets created, or induced, right across the liquid. It's a very tiny voltage, but it's there. And it gets picked up by 2 small electrodes that are mounted on the wall of the pipe, just waiting to measure it.
All right, so we've got the science principle down. Now let's take a look inside and see how these ideas actually come together to build the meter itself. You might be surprised at just how straightforward the construction is. Believe it or not, you only really need 3 key parts. First, you need an electrically insulated pipe. It's often made of fiber or has a special lining, and that's just to make sure the voltage doesn't leak away. Second, you have those 2 electrodes placed opposite each other to pick up the voltage. And third, you have the magnetic coils on the outside to create the field. That's the whole thing. Okay, we've got the science, we've got the parts. Now let's put it all together. Let's see how this thing actually works in practice.
And you know what? The relationship here is super simple and direct. It goes right back to Faraday's law. The faster the liquid moves through that magnetic field, the more voltage it generates. So if the flow is slow, you get a low voltage. If the flow is fast, you get a high voltage. Simple as that. So here is the most important thing to remember. The voltage that the electrodes pick up is directly proportional to how fast the fluid is moving. So by measuring this teeny tiny voltage, we're often talking just a few millivolts. The mag meter can calculate the exact flow rate. It's incredible. No moving parts, just pure physics at work. Now, of course, like any piece of tech, it's not the perfect solution for every single situation. So let's be fair and take a balanced look at both the pros and the cons of using an electromagnetic flow meter. The advantages are really compelling. For one, it can handle those tough slurries and corrosive fluids we talked about no problem. And its readings aren't messed up by things like viscosity or pressure changes. It's also great for measuring extremely low flow rates, and it even works as a bidirectional meter, meaning it can measure flow in either direction. Pretty cool, right? But on the flip side, the accuracy can sometimes be a bit lower than other types of meters. And when you're dealing with really big pipes, these things can get pretty heavy and large in size.
So what's the big deal? Why does this all matter? Well, it matters because this technology lets us measure and control industrial processes that would just be impossible otherwise. It gives us a safe and really reliable way to handle these very difficult liquids. That means better efficiency, better safety, and you don't have to worry about a mechanical part breaking down.
And all of this leaves us with a final question to think about.
We know these meters are absolutely crucial in places like wastewater treatment and food processing. But where else could this kind of no-contact measurement be a total game changer? What other tough industrial challenges do you think a device like this could solve? It's really fascinating to think about the possibilities, isn't it?
So there you have it. The electromagnetic flow meter, all explained. I hope you found this useful. If you did, please do give this explainer a like, and maybe share it with someone you think might find it interesting. And of course, don't forget to subscribe to Kognito Key for more deep dives just like this one. Thank you so much for watching.